Okay, this is going to be just a short video to demonstrate how to apply Newton's method on a TI calculator. This is a TI-84, but this works just as well on a TI-83. So just for the sake of this example, I'm going to be showing how to approximate the square root of 2. So x is the square root of 2, therefore x squared is 2. X squared minus 2 would then be 0, so we're going to use x squared minus 2 as our function. Its derivative is 2x. So using the Newton's method formula, our next guess will be a function of the previous guess. This is the recursion rule we're going to use for Newton's method. It's the previous guess minus a ratio, where you take the f of x divided by f prime of x. Okay, so for this demonstration, I'm going to use an initial guess of x0 equals 3. All right, so picking up my TI calculator here, first thing I'm going to do is take 3, and I'm going to store that. This is the store button right here, stow. So I'm going to, on the screen you see 3 arrow, and then I'm going to store it in the x variable. And x, you can obtain x with this button. This button does different variables depending on the context, but out here in the home screen, it does x. So you do 3, store that in the x value, and then now this just says 3. So now, whenever I use x, it's equal to 3. All right, so now what I want to do is type in my formula here. I'm not going to use xn, I'm just going to use x in place of this. So it's going to look like this, x minus, and then a fraction. So I'm going to start a parentheses here. Oh, and actually, before I go on, hang on, let me clear that. I'm going to wrap this entire thing up in parentheses so that I can store the entire thing. So here we go. Starting over, x minus, and then we're going to do a fraction. So, parentheses, x squared, and then minus 2. Close the parentheses, and then divide that by, again, I want to open parentheses, 2 times x and close parentheses. Make sure you put parentheses around that 2x, by the way, so that you are doing the order of operations correctly. All right, so there we go. So there's our formula typed into the calculator, and if I just hit enter, what that will do is it'll calculate x1. So that was x1. I can write here x1 equals 1.83 repeated. All right, but having typed it in that way, I don't have quite, it's not going to be quite as convenient as otherwise would be. So let me get that back. I think I do second enter, right? And I get the previous thing I wrote down. There we go. So what I want to do is evaluate that again, except I want to then take the value I got and store it back in the x variable. So having that entire expression stored in x, now if I hit enter, it's going to evaluate that expression, but it has also stored 1.83 repeated in the x variable. So if I bring it back and hit enter again, now it evaluates x2. So I can write x2 is 1.46, and then it looks like 21212121. It looks like the 21 repeats. Now on a TI, you can hit second enter to get the previous thing you had, right, like that. But if you just hit enter, it automatically just reevaluates the exact same expression you just did. So in fact, what we can do is just hit enter, 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 enter. And that is going to continue reevaluating that expression over and over. So now what we see is we're seeing the numbers starting to repeat. And so the fact that it's repeating means that it's getting so precise, or so accurate, I guess. I always use those words wrong. In this case, it's getting so accurate that the difference between these numbers is not visible in the limited amount of decimal places that we can actually see here, right? Like the difference between these numbers is so small that it would exist. We would see the difference further along the decimal expansion, somewhere where, further down there. So yeah. So our degree of precision that we're seeing this with is not sufficient to see the difference in accuracy. That means we must be really, really close. So the result here is the square root of 2 is approximately equal to this number, 1.414213562. And that's very accurate.